One thing we haven't really talked about a lot is images, because we've been talking about tools and applying those tools. And I hope that you see that these tools can be applied to images and to signals and to all forms of data. But since we're talking about neural nets, let's actually talk about what the input is. Well, what is the natural thing to do? We've got our inputs over here, we've got the hidden layers, we've got the output, and let's say we're trying to do a classification like, is there a cat in this image or not? Is there a face in this image or not? First thing you got to ask yourself, before you ask yourself how many layers and what is the connectivity and what is the nonlinearity, you got to ask yourself is, well, what am I feeding into the network? Well, the natural thing to do is feed in pixels. What else are you going to do? Display an image, you got a bunch of pixels, black, white, color, I don't care, whatever it is. And that's sort of the natural thing to feed into the network. But it's not at all obvious that is the best representation. After all, each pixel, there's a lot of redundancy. Pixels in a neighborhood are actually, pretty similar, for example. Like here, there's a lot of similarity. And if you remember when we were talking about hog features and edges, there is a lot more information you can get from running things like simple convolution filters, like the gradient or the derivative filters. And so convolutional neural networks are a nod to the fact that maybe, just maybe, feeding raw pixels into a network is not the smartest or most efficient way to do things. And what convolutional neural nets do is they start with a simple grayscale or color image, and they learn convolution filters. That's this step here. What are the filters that we apply through a convolution? Nothing more complicated than linear transformations again. And then there's often a pooling step, which means you're just going to downsize the image to reduce the complexity because these big images cause huge amounts of problem. And then you take this downsized convolved images and you flatten them out into a bunch of inputs, and then you push that through your neural network the way you would normally do in everything we saw before. And so what you're doing here is you're saying, what we used to do back in the days, we would assume that the gradient or the hog or the sift or some other pre-processing step was the quote-unquote right process. But there's no reason to have to assume that. And what convolutional neural nets do is they learn the full pipeline. What are the kernels, the filters we should apply to the image? And you can see here maybe more than one. Here I've done 4 of them. Again, the downsizing is to reduce complexity. And then what gets fed into the neural network is this learned filtered representation from which training, the hope is, should be easier. And here, the game is sort of similar. You've got the same problem. You have to learn these weights, you've got backpropagation, and you've got all the tricks that lie on top of that to make these things efficient and to try to extract the information that you want. So here's the good part of neural nets. The good part of neural networks is that they're powerful. They're incredibly powerful. In fact, the universal approximation theorem tells us that they're as powerful as you need. The downside is that they are data monsters. You need massive amounts of data to train these things. And the reason, of course, is that in fully connected, deep networks with multiple layers and all fully connected, you've got, in some cases, millions, in some cases, tens of millions of degrees of freedom. And to train that in a way that will generalize to new problems means you need massive data sets, or you need to be very clever on how you augment your existing data set. That's the bad news. The other bad news is that these neural nets essentially act as black boxes. It is very, very difficult, if not impossible, to truly understand what is happening inside of these neural networks because of the complexity of the calculations as they make their way through the linear models and the nonlinearities and the interconnections between them. And so when things fail, it's hard to know why they failed. And so it's a bit of a double-edged sword. On the one end, we have least squares estimation that is clean, well understood, analytic, efficient. We know what the assumptions are. When it fails, we have a pretty good idea of what's going on. It's just not satisfying the linear model. It's not a problem of the optimization. On the other hand, we have neural networks, deep neural networks, convolutional neural networks, which have a phenomenal amount of computational power, but are very, very hard to train, require GPUs, require massive data sets, and when they fail, we don't necessarily know. And in between is a bunch of other stuff like nonlinear SVMs. My suggestion to you is don't jump to the neural nets. Start with the simple techniques, the simple classifiers, and add complexity as you need complexity. In some ways, you use neural nets when you've given up all hope. When you say, I have no way of understanding this problem, I'm going to let the neural net figure it out. But the more interesting scientific and really engineering perspective is to say, I'm going to try to model whatever it is that I'm trying to compute, and I'm going to bring to bear the necessary tools without having to revert to this very, very complex machinery. I'm not dissing neural nets, don't get me wrong. I think they have a time and a place, but I think we should understand that time and the place. Now, at this point, it's unlikely that you can take what we have learned about neural nets and then just go deep into them. But what I hope you have learned is what the underlying structure of a neural network is, which is actually relatively simple in terms of a linear model, pointwise nonlinearity, and then multiple connections through these multiple neurons and hidden layers. All the complexity of neural networks is how you do the optimization in order to learn all of the weights associated with it. And that requires a little bit more knowledge on optimization and then a lot of practical experience of training these things, understanding what works and what doesn't work.